Howdy there. Let's talk about anomaly detection. I think you just got an anomaly. You guys were thinking you could read email for another 10 minutes. Not going to happen. So, what I'd like to do is talk today about how to find what you don't know what to look for, the real anomalies. Not the ones that you already understand, but the ones you haven't seen yet before. Those are the fun ones anyway. So I'm going to talk a bit about what anomaly detection is, going to give some examples, and then I'm going to generalize the examples, and drop into a little bit of philosophy about the fact that compression is truth. At least one person here will laugh about that. Thank you. Then we're going to drop into some deep learning and talk about the parallels between some of the very, very simple things we've seen as examples up to that point and this whole new area of deep learning. There's a lot of exciting stuff going on in this area. And then I'm going to drop all of that and say why anomaly detection drives toward better time series databases. I'm Ted Dunning. I'm Chief Application Architect for MapR. We make kick-ass Hadoop distribution. That's the technical term. It's a technical talk, so it's okay. I'm a committer, a mentor, champion, a lot of things on many Apache projects. Been involved in open source for many, many years. And today, we got a hashtag, Hadoop Summit. Let's do it. We also, by the way, have a book. I'm glad this slide's in there because I would have forgotten. A little tiny book talks about anomaly detection, the stuff that's in this talk, at least at a slightly more introductory level than what we'll be doing today. And Ellen and I will be signing books there. You can see Ellen in the picture there, at least her thumb. You'll recognize her that way. She's an international hand model and author. So we'll both be there, so you'll get to see the rest of her, at least some of the rest of her, at about 4 p.m. between the two talks that I'm giving today. So the first question here is we want to find out about anomalies. Anomalies are things that just happened that shouldn't have. But you can't enumerate all of the things that don't happen or all the things that shouldn't happen. There's just too many things in the universe. And in particular, I take the point of view here that I used to have very, very particularly of somebody who wants to find these anomalies before somebody else does, notably my CEO. And this work germinates a number of years ago where I had a hyperactive CEO, and he would not sleep through the night. He would wake up at 2 in the morning and he'd go check all the metrics, and he would say, and he'd call me and he'd say, Ted, we haven't had a sale in 5 minutes. Do you think that's okay? And you know, in those sorts of moments, the only possible answer somebody can give is, huh? What? Because you're not awake at that point. You have no idea really who it is who's calling or anything like that. So what we wanted to do is build a system that would call me first and give a dashboard for the CEO. So when he called, his delayed dashboard would just barely be turning orange. And he'd say, Ted, the dashboard's turning orange. It may go red. Is this okay? And I go, Dennis, where you been? I've been on this for 10 minutes. It's over. We got it covered. And it wasn't too long after we started doing that and having those alerts go to the ops staff first that he started sleeping through the night. And this is a very, very important phase for CEOs to get through. You have to work with them, train them very carefully, make sure they sleep through the night. Because if you don't do it when they're young, it just will get out of hand later. But of course, I didn't want to be woken up if it wasn't really broken. I didn't want to just make an automated CEO. I wanted something that really did wake me up when there was a good reason. So that's what we're going to talk about here at the beginning, is how we did that. So if we have something, this is random noise, but other things look kind of like random noise, and this random noise seems pretty well characterized, at least from what we can see here. It's got a nice level to it. It's got a certain level of fuzz on it. It's got no bizarre behavior there. And so if we see that happen, looks like an anomaly. The idea there is that it's violated our brand new sense of what normal is. Now, it isn't always that simple. So for instance, which one is the anomaly here? Is it the little spike? Well, if we see spikes on top of the fuzz, characteristically, if that's just what happens, we could include that in our definition of normal. And at that point, the step on the right would become the anomalous thing. Or if spikes never happen, both of these could be anomalies. The key question of what is an anomaly depends on what normal is. And normal's really a judgment sort of call. So we want to take action when something breaks or otherwise misbehaves or just behaves outside of our experience. We want to avoid taking action because it's expensive. And we don't want false alarms. We do want true alarms. We need to trade off the costs of having to wake up in the middle of the night for no reason and the cost of the CEO actually finding something real. Both are very serious, and we have to do that. So if we take a look at this, we could adaptively walk along that signal, and we could decide what an acceptable threshold is. We could say, like, the 99.9% threshold. That means that if that really is that quantile of the true normal signal, we know how often we'll get an alarm. There's two ways of doing this. You can set a budget. I'm going to be woken up 3 times this month. I know it. I hope that as many of them are real as possible, but I'll let the system wake me up that often in order to find as many faults as possible. The other thing is anomaly driven, where the cost of missing an anomaly is so bad you just won't miss any. So there you set a false negative rate. This is a very common situation where you set your total budget. So that's one thing we can do. We could automatically set that threshold. And in fact, there's software that does that. A thing called the T-Digest we worked on recently can do online summarization of the entire distribution over history. And you can set a threshold in terms of percentiles. And then it can just check it. So, I mean, at slide number 12, we're done, right? Well, maybe not. Maybe there's a bit more to do there. It looks like a solved problem at this level of difficulty. Indeed, there's software called Skyline, and it does basically this thing, except that you have to set the knob yourself. So here's an example where this isn't going to happen. We're going to find very easily this anomaly, the one at A, or that A for you guys, but we're going to miss this B because it's sitting in the valley. No single threshold is going to differentiate B from normal behavior. We're going to have to track somehow. We're going to have a more nuanced idea of what normal is. Or if we look at this signal, there's an anomaly there, it looks like. I mean, it's just like the previous anomaly. But in fact, it's not so good because I don't call those anomalies, I call those heartbeats. And I am rather attached to those. If the CEO calls and said, your heart just beat, I would be really upset with him for waking me up because I don't want that to be an anomaly. Instead, here's an anomaly in a heartbeat. Somebody has an irregular heartbeat. These are real signals. This is a real person. This guy's got some problems. So we need a much more advanced sort of thing, not only to find that hills and valley kind of signal, but to find this kind of thing, where it just behaves wrong. It doesn't look like a good heartbeat. So what we want is a model of normal that's flexible enough to find all these things. For the simple signals, we can just say the model is its normally distributed noise. The real world never works that way. So let's take a look at one way to take apart that EKG signal, the heartbeat, and build a really interesting model. Not necessarily the epitome of all models for a heartbeat, but a much more interesting one, and really a pretty simple approach. So what we'll do is we'll take the original signal, that's up at the top, and we'll multiply it by this signal, which is called a window. The reason it's a window is because it's 0 everywhere except inside a little window. And it goes smoothly to the edges, and it snips out a characteristic little bit, 32 samples of non-zero signal out of that original. And you can see that shape right there, but the shape just after that, the shape before it, have been removed. Okay, that's no big deal. And then we can move that window, and we get other signals. And in fact, right there, we see something a lot like that first one. And right there, we see another one. And Right there we see another one. So we see very, very similar little shapes appearing within this window because this is a very repetitive signal. We see those shapes again and again. And what we can do is we can take those windowed signals and we can use something as simple as clustering to find kind of the Ur shapes, the things, the archetypes of heartbeat shape that describe that. Now, the cool thing is that windowing function that we picked happens to have a very nice property that when you shift it by half and add it back up, and shift it by half and add it back up, and shift it by half and add it back up, just like we did, the signal adds, or the window adds to 1. And that means if we recombine all those windowed signals that we got out at the bottom, we can just add those back up and reconstruct our original signal. Likewise, if we reconstruct each little window full independently and put those back together, we also get a reconstruction of the original signal. That's just what that, well, these are the shapes that this particular run came up with. There you see that's very much like the signal that we saw in the first slides, except these are slightly shifted. And here is an example of that reconstruction. There's the original at the top. There's the reconstruction in the middle. And by the way, it only takes about 1 bit per sample to encode this central signal. It takes even less if you use slightly more interesting statistics. But here is the reconstruction error. Very small on average, except when there are very, very sharp slopes, which are very difficult to reconstruct exactly anyway. And the reconstructed signal looks just a whole lot like the original. The only thing missing are little bits of fuzz for the most part, or very slight shifts in exactly when those attacks occur. So we can reconstruct it, and we can get reconstruction error, and we can continue scanning along, and take a look at this right there. That reconstruction error just kind of went to hell in a handbasket right there. And the reason it did is because that right there doesn't look like a heartbeat. Now, it does at the resolution we see here, but the system is unable to reconstruct it accurately, so we get a large reconstruction error. And if we magnify that, we can see that that's incipient atrial fibrillation. That's also known as bad for you. Not a good thing at all. So this system, as simple as it is, has found an interesting physiological anomaly that would even be hard for a human to find. So we've taken that and we've built a statistical model. Here's another anomaly. Now this is quite the anomaly. It looks like a lead came loose. It's not a physiological anomaly. It's not the guy's heart that's a problem. It's the measuring system. But it also does not look like a heartbeat, and that's what the system says here. That doesn't look like a heartbeat. I can't reconstruct it at all, and so we get this huge reconstruction error. So the system has a very, very detailed and nuanced view of what a heartbeat should look like. In the first example, with just the random noise, we had a very simple idea of what the signal should look like. It should look like that, right there, plus or minus a little bit. Here, we want it to look like a heartbeat, like the dynamics of a heartbeat that they occur. And so we can build a different kind of anomaly detector by putting a model in there. The model is doing reconstruction there. We're subtracting off the reconstruction to get the reconstruction error, and now we can treat the reconstruction error exactly as we did before. Still, actually, a very simple anomaly detector, but now looking at quite an interesting signal, a lot of time dynamics in there. And it's finding fairly subtle and grotesque errors in the signal. And you could imagine that it doesn't have to be a heartbeat. It could be all kinds of things. You could imagine a water supply for an entire town, because that signal will have all kinds of correlations, not across different time samples, but across different measurements at the same time. If there's water going into this pipe, there darn well better be water coming out of it. If that sort of correlation is violated, we have a leak. If there's water going in here at a certain pressure and water coming out here at a much lower pressure than we expect for that flow rate, we probably have a constriction. And so a system like this, using k-means or other sort of dimensionality reduction system, could actually detect the normal operating characteristics of a complex machine like that. And it could then quantify the reconstruction error and say, this is anomalous operation or it is not. It wouldn't mind if no input goes in and nothing comes out, that's okay. It wouldn't mind if lots goes in and lots comes out, but it does mind the lots goes in and nothing comes out, or the reverse. So we can build very, very nuanced sorts of anomaly detectors out of such a system. And what we're doing here is building a really fancy probabilistic model. And thinking about probability distributions is a really good way to think about these things. And we can extend it even to not just time signals like this, but event streams. Now, the characteristic of an event stream is not a signal that goes up and down and has intermediate value. It's not an analog kind of thing. The characteristic of an event is when it occurs. Occasionally there's other data attached to it, but the when is what makes it an event. And so we can build a model about whens, or perhaps differences between whens. And we can do that using variable rate Poisson models, things like that. By the way, these slides are pretty much all in the book, so you don't have to take the pictures. It's fine if you do so. And it turns out that we can do just the inter-event arrival time and an estimated rate. And we can get a very, very good anomaly detection even out of event signals without the continuous variables. So far we've seen how to build anomaly detectors. That's pretty cool. And furthermore, we've seen the value of building a good probabilistic model for understanding what is likely to occur and what is not likely to occur. Different systems require different models, of course, and there's different ways of attacking these depending on what kind of signal you have. But the case remains. It's still good to do probabilities. But there's a very interesting thing about this, because if you build a good anomaly detector, that allows you to differentiate probable from improbable. To do that accurately, you have to have a good probability model. But it's an interesting mathematical thing. In fact, information theory is grounded on this simple fact that if you have a good probability model, you can compress it well. And in fact, the thing that gives you the best compression is identically the best model at predicting what's going on. So minimal error is maximum likelihood is maximum compression, and so really good anomaly detectors are also very closely related to very good compressors. And if you care, that this is in there for reference later. I don't expect everybody to go wickety through those equations, but it's actually a very straightforward and simple derivation based on this observation that the log has this property of being maximum relative to that linear property, and it's always concave downward. Now, if we stop to think about clustering, because that was pretty prominent in the way we built these models so far, it's a little bit different from the way people usually think about clustering. Finding the nearest cluster for each window, we could say distance, Euclidean distance. That's the way those are normally implemented. But you could as well say dot product, because in this case, all of the clusters were normalized by magnitude. And so dot product is equivalent to distance. It's upside down relative to it. Big is small and small is big, but it works the same way. So dot product is good there. And we need to scale the cluster to the right size. What's the right size? The right size is, again, that dot product. So we've got a really pretty simple mathematical system. And in fact, we have what's called an autoencoder. It is compressing that original signal down into a very, very few number of bits, and then it's re-expanding it. And the idea is that by decreasing the amount of information, by compressing it, that is finding a good probability model. The one that compresses best is the one that provides us with the sharpest anomaly detection on that reconstruction. But the mathematics of it actually are exactly the same as a very simple neural network, a self-reconstructing neural network. The reason that that works is because the signal coming in here, there are numbers inside these circles. and then there are weights on these lines, which multiply by those numbers, and then we sum them up in the middle circles. Sums of products are dot products. We find the biggest one. This is a 1 of k type neural net. Find the biggest one. That's like finding the closest cluster. And then the reconstruction consists of just those same signals as we used in the dot product on the output. So this is exactly clustering, and it is exactly a very interesting kind of neural net. The reason it's interesting is because we can use it with m of k instead of 1 of k. And at that point, it becomes what's called sparse coding. Found in 1996 to be able to replicate the performance and characteristics of the human visual cortex. That observation has been extended over the last almost 20 years now to systems that can recognize cats. Wow, now isn't that useful? But it's also systems like Android's speech recognition system are based on essentially the same sparsity property. And so we can use sparsity in that way. We can build a little neural network for each window, and then we can slide that across our signal, and we can use that neural network encoding at each step, either as an encoding or as a way to find anomalies. The reconstruction error is the anomaly, and we can store places that have big anomalies, but we could just as well use those bits in the middle, the sparse bits, the cluster assignments, or the m of k cluster assignments, as a representation for the signal. And that's where we get a very interesting form of time series database. As you stack these up, you can still learn these because of that sparsity constraint. And what happens is at higher and higher levels of abstraction, this system learns more and more semantic representations of the signal. So the final interesting line out of this is that this gives us a way to build a time series database which is heavily compressed and remarkably searchable in semantic terms rather than just what happened at this moment. We can actually say, show me all the heartbeats like this one. And we don't have to say what like means. It will automatically find which are the most salient properties, the most unusual properties about this, and find those which have similar properties. We can do that with mechanical systems. We can do that with other systems, flow, properties, loads, all kinds of things, traffic. And that will find anomalies. And it will compress data as a result of finding good anomalies, and it will help us search things that way. So we have, I'd meant to give 15 minutes, but we have 16 and a half. So let's talk about how these compression algorithms, how this compression being truth, and how this semantic search matter perhaps in what you guys are doing, and in particular how you could build one of these systems. We've got a couple folks with microphones, hopefully doing the runaround to try to help you find a voice. Anybody got any comments or questions about this? We can talk also about implementation of these things. Difficult for me to see hand. Is there a hand over there? This is like an auction. If you raise your hand to scratch your nose, you have to ask a question. You have to be very careful. This man does not have an itchy nose. He has a question. Is there going to be somebody on deck? Yeah, Mark there. Yeah.
So I just have a basically maybe more detailed question about these autoencoders, this kind of stuff. They usually have, these sigmoid functions, those kind of nonlinearity in them too. So for these anomaly detection, are you proposing also those kind of nonlinear functions? And if so, do you have some explanation for them, what to do? So, or is it mostly going to be just linear without those sigmoid or similar softmax, those kind of functions?
So the question has to do with how those interior nodes work. I've proposed here in this particular system, just because it worked, not because of any deep philosophical bias on my part, probably a deficiency on my part to not understand I should be biased, but that I use a sparsity constraint. And what I see more and more in the systems that are working very, very well is that the sigmoidal representation is much less important than sparsity-inducing properties. And so to me, the generality that I'm seeing across many different approaches, so there's rectified linear units with sparsity constraints. There's sigmoidal things with sparsity constraints. There are linear things with sparsity constraints. Over and over and over again, the common theme among the very, very successful research is sparsity constraints. And it's a different kind of regularization. Regularization is a way of forcing a system to be simple. The old system would have just said, let's use very few weights, but all continuous, all non-zero, that's fine. And that doesn't work. It just becomes very difficult to learn. What made these things start to work with very, very simple implementations, this is really literally only 100 lines of code or so for the entire stuff. And what makes it work is the sparsity constraint. And so that's what I think is really, really exciting. And that's what's news here that a lot of people haven't heard. Yeah, Mark, and who wants to be on deck after Mark? Raise a hand so Ellen can find you.
Yeah, could you comment on where you have longer range dependencies in terms of the data?
You have to stop moving your hand when you say the good words.
Longer range dependencies in the data.
Long range dependencies, yeah. So Mark, of course, is a sharp cookie, and he caught the quick slide that I did. So the system I had little windows, and it characterized little windows, very short windows, much shorter than a normal heartbeat. So it can characterize shapes within that window, but as stated, the system can't really say this window is next to this other window or 3 down from another window, and their conjunction, their co-occurrence, their contiguity is anomalous. It can only say the one individual is anomalous. Now what happens is as we move up, as we look at the system which says this window number 37, this window number 73, and these codes, we can look at a higher level and re-encode that signal in a sparse way so that it finds patterns, sequential patterns of windows which make sense. And that lets us encode longer and longer range correlations without having to have a very, very high dimensional clustering at the bottom. And this is the way that speech recognition actually happens in these systems. They use 8 or 9 levels so that they can get very long range correlations, which are of course necessary to understand which word I'm saying here based on the words that I might have said just before that, or even just after it, because there's nothing that says speech recognition has to happen at the leading edge of what I'm saying. It could be happening a few words back. And so that context grows as the depth grows. And indeed, the complexity of the sorts of things that you can encode, the interesting complexity also grows without increasing the bit density. And so there's a nice contiguities, co-targeting with the right sort of things that we want to do. Yeah, you got a mic?
Hey.
Okay.
If I understood correctly, when you were talking about the time series databases, if you had a large number of those databases, you alluded to some sort of semantic meaning. So if you wanted to, aside from the reconstruction error, you have the characteristics of each of those time series?
Yeah.
So could you talk more about how you would interpret the semantic meaning, or how you would give them semantic meaning?
Now, keep in mind that I'm the kind of guy who does kind of semantic is as semantic does. If a person who I characterize generously as being intelligent says, whoa, look at that thing, it seems intelligent, then who am I to argue? And so semantics, to me, is that it does an interesting task that a person would attribute to meaning. That's all I mean. And so here, if we have a particular window of this, and inside here we've got this sparse representation, that is a sparse representation, 1 of 400 symbols, say, or a few out of a few hundred symbols. And we have sequence of those sparse representations stacked beside each other in time. Those then are now symbols, and their combinations are also symbols. Now, associated with weights as well, but they are symbols. And those can be treated as such and can be indexed as symbols and associated strings. And that allows us to use things that retrieve symbols to retrieve these. That's pretty exciting. I mean, that's hopefully, I mean, we have one example of how if we just have somebody do all of the bottom layers of perception for us, that this kind of retrieval will work, and that's called text. And all of these carbon units on the planet have very, very kindly donated their time and effort in order to encode these auditory signals in such a way that they handled all the bottom levels, and shazam, we can now do that retrieval. But what I'm proposing is that we can push that retrieval down and automate those lower levels in interesting ways for interesting signals appropriately for the signal. So that's what I'm really talking about there. We have 9 more minutes, yeah.
Is this on? Okay. I have a couple of questions. So first off, in the windowing example, I can't remember, are the windows overlapped? And
yes.
I assume they were overlapped. Okay.
And I'm really proud of the fact that I was able to overlap these windows.
Okay.
That was
This is a
not
little hard
easy to do. Look at that, see that?
Okay.
This is in
Got it.
PowerPoint.
Also, you're dealing with a very periodic signal. Have you considered doing the same windowing in the frequency domain?
Yeah, now this is not a this whole idea of frequency domain and things like that, you know, it's kind of cool and steampunk to talk about 19th century concepts, but this is not a periodic system. This is a kind of periodic system.
Well, I mean, pulses are periodic, right?
Pulses are not periodic. Pulses are kind of periodic. My pulse is increasing in speed.
Okay.
So, you know, that sort of thing. So they don't exactly match up, and especially sick people, they bob around a little bit. Mm-hmm. And in normal people, they get faster, they get slower, they change in their rates. Mm-hmm. Now, they're nearly periodic, but not exactly. Now, the fundamental assumption of Fourier analysis and that kind of spectral harmonic analysis is that things are exactly periodic. They are like a radio wave that is very, very, very periodic, very, very precisely periodic. And the other assumption there is that what we want is a basis space for representing these signals. We have one naturally. That's sample, 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 sample. That's like this one. That's the basis space that I have for these signals. Another one is, as you say, in terms of frequency. And the presumption is that that is good because it's what's called an orthonormal space. It has the minimal number of representation elements in order to represent any signal of the dimensionality that I have. Mm-hmm. And there are compact support things, Dobeshi's wavelets and things like that have similar properties in time so that they aren't this infinite extent. But in fact, those don't work in practical terms very well because they lack this sparsity property. Once I encode a signal into a sine wave, cosine wave basis space or into a wavelet space or things like that, typically I have all coefficients non-zero.
So do you find that the sparsity representation is good with only one layer? Because, so if you look at Hinton's paper about sparse encoding, semantic hashing, there are multiple layers there. He steps down from like 2,000 to 500, et cetera. Are you finding that there's some issues there, or is it okay with just one layer?
Well, it depends on what you're trying to do, but I'll let you tell me, did this produce kind of a cool result? This is one layer, this is sparse, and it found anomalies with just a modicum of training.
Okay.
And it found interesting anomalies. They had explanations, you know, and we understand hearts very well, so we're not finding new stuff, really. We're not advancing the state of the art of medicine. We're not even advancing the state of the art of signal processing here. It's just kind of cool that you can, in a Saturday afternoon, whip out something with just the principle of sparsity and get interesting anomaly detection like that. And you can get compression on the order of what a Karhunen-Lev compressor will do, which used to be the state of the art. Again, with no effort. to speak of within round-off noise. Yeah.
A quick comment on the Fourier analysis. You could have used wavelets as well. So that's one other way of doing it. But have you considered symbolic approximations? So reducing the dimensionality and cardinality of your data, symbolic aggregate approximations?
So wavelet expansions generally are defined again with a minimal set of linearly independent signals. Minimal orthonormal space subject to translation.
Right. That was about the assumption of periodicity, which you don't need to use a
you're
Fourier
right,
domain.
You're right.
But
Wavelets get rid
regardless
of
of
periodicity.
that,
That's correct.
You could use different methods for symbolically approximating the time series. There's a number of papers from UC Riverside on using symbolic aggregate approximations that basically translated the time series into a sequence of letters. And that method preserves a very important property, which is a lower bound property. And so have you ever explored any of those venues?
I have, and never had results as easy as this or as good as this. And the Riverside group, the SACS encoders and things like that, are assigning these letters according to basically heuristic properties. And they're good in certain high noise environments, but in general, they're not as effective for building large-scale, interesting systems. And they have some, I think, very, very good insights in there. I think that they're just weighed down by some of the other things that are not as good in insights on what they're doing. But this is effectively a symbolic representation. If you think about it, it's 1 of 400 symbols. That's how many clusters I have. And so it is a symbolic representation. And so it does inherit some of those properties, the good properties, of some of these other symbolic properties, systems. But the key here against most wavelet systems is the sparsity. That's what makes this simple and good. We have 3 minutes. Got a 3-minute question? Oh, here's a 3-minute question. The man asserts so. Just in case, is there a 30-second question behind it?
So the question is, how do you choose the window size for your wave?
There's a special procedure that I go through, and
Is it called guessing?
kind of like that. No, it wasn't exactly guessing. It wasn't exactly more. But I looked at this heartbeat, and I said, looks like pieces are kind of like that big. And I said, how fast are these samples? That's 32 samples. I love powers of 2. Let's do it. And all of the choices that I made here were made in similar disregard to any sort of philosophical purity or mathematical propriety. I chose 400 clusters because 400 seems like a lot. It's not little, it's not 32, and it's not a massive amount.
It's not a power of 2.
It saddened me deeply. I realized that afterwards. And I show my heritage as a primate in that I like zeros on the end as well. But the fact is I chose 32 and I chose 400 just out of the blue. And the system worked great. And changing later the number of clusters between about 100 and about 800 made no perceptible difference to the system. So these things, in contrast to many neural network systems, seem to be quite robust to turning the knobs in random ways, which is very good because I lose interest very quickly. And so great amounts of knob tweaking would have just totally lost me. So we have 1 minute more. Here's a 1-minute question over here, if you could. Okay, somewhere back there. Say it.
Could you talk about the performance complexity of the method you used, specifically just with relation to Hadoop, I guess?
So this is, as far as parallelization is concerned, this is in a class of embarrassingly parallel problems. And the reason it's embarrassingly parallel is twofold. One is the fundamental reason is because we each have our own heartbeat. And you can analyze your heartbeat in isolation from mine. That means we can parallelize the analysis of these. Now, the initial construction of that clustering is somewhat less parallel, but there are single-pass parallel algorithms for k-means clustering, which are essentially perfectly parallel. And so that maps to MapReduce very easily. Once we have the dictionary, once we have the model, then processing your heartbeat can be done in faster than real time, vastly faster than real time. Processing mine can be done vastly faster than real time. And in fact, we can process everybody in their own little map invocation. And so it becomes not even a MapReduce program, it becomes a map program. And so the database insertion problem is again, trivial. It's perfectly suited to Hadoop MapReduce. Even MapReduce is sufficient. No need for fancy stuff at all. We have 30 seconds for this fellow here.
Window curve?
That was a Hamming window, so that's the sine squared. And sine squared, of course, shifted by a bit is cosine squared. Sine squared plus cosine squared is 1. We win. And, you know, I guess there's just more evidence that Hamming was a pretty clever guy. But we knew that, didn't we? Well, thank you very much. This has been a great time to talk to you.